Welcome back, everyone, for another deep dive. This time we're tackling a concept that's becoming increasingly crucial in the world of AI, mechanistic interpretability.
Exactly. It's about going beyond just knowing that our AI models work. It's really about understanding the why and the how behind their decision making.
And for our listeners, they're all experts here. This isn't about basic input-output. We're talking about getting a glimpse into the actual representations and algorithms the model is using.
Right, and to really dig into this, we're going to be focusing on a specific tool that's been generating a lot of buzz in the field. Sparse Autoencoders, or SAEs for short.
SAEs, they're kind of like giving us a way to peer into the black box, to break down those complex neural activations into smaller, more interpretable features.
And what's really fascinating is that SAEs are helping us move beyond that simplistic view of AI as just a supercharged pattern matcher. I mean, we're seeing evidence that these models are doing something far more nuanced and complex.
Right, those aha moments that challenge our assumptions. Like, tell me about this whole multilingual and multimodal features thing.
Absolutely. So research has shown that the same features in these models can light up in response to the same concepts, even when they're presented in completely different languages.
Really?
Yeah, and the classic example is the Golden Gate Bridge feature. It activates not only for textual descriptions, but also for images of the bridge. And get this, it doesn't matter what language is used.
Wow. So it seems like these models aren't just memorizing surface-level patterns. They're actually developing some form of deeper understanding.
It really raises the question of how these concepts are actually represented within the model. And one of the biggest challenges we face is that these representations, they just don't map neatly onto our human way of thinking. We have this phenomenon called polysemanticity, where a single neuron can respond to multiple seemingly unrelated concepts.
Okay, so it's not a simple one-to-one mapping between neurons and concepts.
Definitely not. And to make things even more intricate, many concepts are distributed across multiple neurons.
Okay, I'm starting to see where the complexity comes in.
Exactly. And this all leads to the idea of superposition, where multiple concepts are essentially packed into the same representational space within the model.
Superposition. That sounds incredibly complex. So how do we even begin to disentangle this web of overlapping concepts?
That's where SAEs come in. They act as a sort of filter, allowing us to identify the most salient features and separate them from the noise.
So we're using SAEs to essentially decode the AI's internal language to identify those key features that are driving its decision-making process.
Exactly. And what's really exciting is that it's not just about passive observation. With SAEs, we also have the potential for intervention. We can actually use these features to manipulate the model's behavior in very specific ways.
You're talking about steering vectors, right? The idea that we can use simple mathematical operations to nudge the model's output in a desired direction.
Exactly. So, for example, research has shown that it's possible to take a neutral sentence, and by manipulating specific features, you can actually shift its sentiment to be more positive or negative.
It's like we're not just observing the model, we're actually interacting with it at a much deeper level.
Right. And then there's that fascinating discovery of the refusal vector. It's a single direction in the model's representational space that seems to govern its tendency to refuse harmful requests.
That's incredible. It really highlights the power of SAEs to pinpoint those high-level behaviors and trace them back to specific elements within the model's internal representations.
Absolutely. But it's important to remember that SAEs aren't a monolithic tool. There's actually a whole family of different SAE variations out there, each with its own strengths and weaknesses.
So there's no one-size-fits-all SAE.
Right. We have variations like jump-rel utopk and even transcoders. The choice of which SAE to use really depends on a number of factors, including the specific research question, the scale of the model being analyzed, even the computational resources available come into play.
So for our listeners out there who really want to dig into the nuances, the effectiveness of an SAE can also be influenced by things like how frequently a feature appears in the training data and the overall scale of the model. This whole concept of feature completeness is definitely worth exploring further.
Yeah, it's a key consideration when evaluating the robustness and reliability of our interpretations. But before we get too lost in the technical weeds here, I think it's important to step back and consider the bigger picture. How are these SAEs being applied to solve real-world problems today?
Right, let's get practical. Our listeners are eager to hear how these tools are making a real-world impact. We've talked about the theoretical underpinnings of SAEs, but what about the practical applications? Give me some examples of how these tools are actually making a real-world impact.
One of the most promising areas is bias mitigation. Researchers have successfully used SAEs to identify and even remove gender-related features from models that were trained on biased datasets.
So we're not just talking about observing bias, but potentially correcting it.
Exactly, and that's huge. By identifying the specific directions in the model's representational space that correspond to these biases, we can actually intervene and potentially nudge the model towards fairer outcomes.
It's like we're using SAEs as a scalpel,
Mm-hmm.
precisely targeting and removing those unwanted biases.
That's a good analogy. And the applications go way beyond debiasing. For example, SAEs could also help us tackle the problem of hallucinations in language models.
You mean those instances where the model generates outputs that are factually incorrect or just plain nonsensical?
Exactly.
Yeah, that's a major concern, especially if these models become more integrated into our daily lives. So how might SAEs address this?
Well, some researchers are exploring whether specific features within the model might be correlated with a higher tendency to hallucinate. And if we can pinpoint those features, we might be able to intervene and reduce the frequency of these errors.
So it's like identifying the parts of the model that are prone to flights of fancy and then grounding them in reality.
Exactly. And beyond fixing problems, SAEs could also be used to enhance the capabilities of these models, particularly in terms of steerability.
You're talking about the ability to more precisely control the model's output, to guide it towards a specific style tone or even level of creativity.
Precisely. Imagine being able to fine-tune those creative dials, not just through prompts, but by directly manipulating the features that govern those aspects of the output.
It's a powerful concept. But with that power comes responsibility, of course. We need to ensure that these interventions are made with a deep understanding of the potential ethical implications.
Absolutely. As we move from being mere users of these models to becoming their architects, we need to proceed with caution and foresight.
Now, all of this sounds incredibly promising, but I imagine there are still significant challenges to overcome. What are some of the biggest hurdles facing researchers in this field?
One of the biggest is the sheer computational cost of training and analyzing these models. SAE research is very resource-intensive, requiring massive amounts of data and processing power.
So we need better infrastructure and more efficient training methods if we want to scale up and tackle even larger and more complex models.
Exactly. And there are definitely trade-offs to consider. Do we train the SAE on the entire model or just specific later? Each approach has its advantages and disadvantages in terms of the depth of analysis we can achieve versus the computational resources required.
Sounds like a classic balancing act between ambition and feasibility.
It is. But thankfully, there are some exciting initiatives aimed at making this technology more accessible. Projects like Geoscope are working to democratize access to high-quality SAEs, allowing researchers around the world to contribute to this field.
That's encouraging news, because this isn't just about advancing our theoretical understanding. It's about shaping the future of AI in a responsible and beneficial way.
It's about ensuring that as these models become more powerful and pervasive, we have the tools to understand and guide their behavior in a way that aligns with human values.
Speaking of understanding, we've touched on some of the different types of SAEs, like jump ReLU and top K. Can you break down some of those variations for our listeners and explain the key differences between them?
Sure. So the core idea behind all SAEs is to decompose the model's complex activations into a smaller set of interpretable features. But they differ in how they achieve that sparsity. For example, jump ReLU uses a specific type of activation function, and that helps create a clearer separation between active and inactive features.
So it's like sharpening the focus of our microscope, making those individual features stand out more clearly.
That's a great way to put it. Top K, on the other hand, takes a more direct approach. It simply selects the top K most active features and zeroes out the rest.
It sounds straightforward. Does that mean it's always the best choice?
Not necessarily. The choice of which SAE to use really depends on a number of factors, like the specific research question, the scale of the model, and even the computational resources available.
It seems like there's still a lot of experimentation and exploration happening in this field. What are some of the open questions that researchers are grappling with?
Well, one of the big ones is how to determine the optimal number of features to extract. If you have too few, you might miss crucial information. But if you have too many, the results become overwhelming and difficult to interpret.
It's a Goldilocks problem. We need to find that just right balance between sparsity and completeness.
Exactly. And then there's the question of feature stability. How consistent are these features across different training runs, different data sets, or even different models?
That's crucial for reproducibility and for building a solid foundation of knowledge in this field. We need to know if the features we're identifying are robust and reliable.
Absolutely. And then there's also the ongoing debate about whether these features represent true units of computation within the model.
Meaning, do they correspond to distinct concepts or operations that the AI is performing? That gets to the heart of what we're trying to understand, right?
It does, and it's a question that we're only beginning to answer.
It sounds like a whole universe of possibilities waiting to be explored within this field. What are some of the future directions that you're most excited about?
Yeah, it really feels like we're on the verge of a new era of AI research, where we're not just building these incredibly powerful models, but actually starting to understand the language they speak.
It's a paradigm shift for sure. And as we kind of delve deeper into this uncharted territory, there are certain areas where SAEs hold immense promise. Like you mentioned earlier, the whole issue of AI safety is a big one.
Right, as these models become more sophisticated and autonomous, we need to ensure that they operate within the bounds of human values and that they don't pose unforeseen risks. So how can SAEs contribute to that?
Well, SAEs could play a crucial role in monitoring for any unexpected behavior, potentially even predicting and preventing those Sydney scenarios, where the AI kind of goes off the rails.
Right.
By analyzing the model's internal representations, we might be able to detect subtle shifts or anomalies that could signal a potential problem. So using SAEs as an early warning system to flag potentially harmful behaviors before they even manifest.
Exactly. It's about moving from reactive to proactive safety measures. And this is where the ability to intervene to steer the model's behavior becomes even more critical.
So if we can identify those features associated with undesirable behaviors, we might be able to manipulate them to actually mitigate the risk.
Precisely. And it's not just about safety either. SAEs could also help us unlock even greater capabilities within these models. Imagine being able to enhance their creativity, their problem-solving abilities, or even their ability to learn and adapt to new situations.
It's about pushing the boundaries of what's possible with AI, while ensuring it remains aligned with our goals and values. But all of this hinges on our ability to continue advancing the field of SAE research.
And that's where the real challenge lies. As we've discussed, training and analyzing these models is incredibly resource-intensive. We need continued investment in infrastructure, more efficient training methods, and really collaborative efforts across the entire research community.
And this is where initiatives like Geoscope are so important. They're working to democratize access to high-quality SAEs, empowering researchers around the world to contribute to this critical field.
Yeah, these open source platforms are essential for accelerating progress and ensuring that the benefits of SAE research are shared widely. It's not just about academic exploration, it's about shaping the future of AI in a way that benefits all of humanity.
So for our listeners who are eager to learn more, and maybe even contribute to this exciting field, where would you recommend they start?
Well, there are some fantastic resources available online. The Arena tutorials offer a really hands-on approach, with coding examples and clear explanations of the core concepts.
And for those who prefer a more visual and interactive experience, Neuronpedia provides a really user-friendly way to explore and understand these sparse autoencoder features.
Absolutely. And I encourage everyone to, explore these resources, experiment and ask questions. The more minds we have engaged in this research, the better our chances of navigating the future of AI responsibly and ethically.
It's a future full of both extraordinary promise and potential peril. But with tools like SAEs, we're gaining the knowledge and the power to shape that future in a positive direction.
It's a journey of discovery for sure. And we're just beginning to scratch the surface of what's possible.
Well, thank you so much for joining us on this deep dive into the fascinating world of sparse autoencoders and mechanistic interpretability. Until next time, keep exploring, keep questioning, and keep pushing the boundaries of AI.